I consider that I understand an equation when I can predict the properties of its solutions without actually solving it. These words from Paul Dirac, a pioneer of quantum mechanics, may seem bold. One could discount the assertion, but not the reality it sits on. Solving an equation can often be a mechanical process, practiced and honed for speed. But arriving at correct and meaningful solutions requires something more: the ability to anticipate the nature of the solutions even before solving. More importantly, when forming an equation from a real-world situation, this predictive understanding becomes essential. It is not just about solving, but about seeing ahead. First and foremost, let's acknowledge that trigonometric equations are often seen as some of the most intimidating problems in mathematics. This lesson aims to tackle that fear head-on, offering a focused and empowering narrative to understanding and confidently solving trigonometric equations. We'll also revisit key concepts from earlier lessons to build a strong, connected understanding that supports success with these equations. Let us begin by exploring how trigonometric equations are constructed, using a few examples to guide us. These examples serve to remind us of two key ideas. First, trigonometric functions are periodic. This means their values repeat in regular intervals, specifically every 2 pi radians. Whether there's one solution or two in a given cycle, the same pattern repeats every 2 pi. Importantly, while the quantitative values repeat, the signs may change depending on the quadrant, so we must pay close attention to sign. Second, angles can often be expressed as the sum or difference of two angles. In such cases, only a few core trigonometric identities need to be remembered to simplify or solve expressions. Beyond these ideas, there's little additional theory behind trigonometric equations. It's mostly about building fluency through practice. Of course, the assertive practice advice comes on the back of the foundation of trigonometry, as attempted through the past 9 lessons. This is a unit circle with a radius of 1 unit. Now, imagine a point on the circumference of the unit circle. Draw a right triangle from this point using the central angle theta. The hypotenuse of that triangle is the radius, so it's 1. The side along the x-axis, that's the adjacent side. Now, because the hypotenuse is 1, cos theta is simply the length of the adjacent side. That's why cos theta directly gives the x-coordinate of the point on the circle. We call it a percentage or proportion of the radius, because it tells you how far along the horizontal axis the point lies, scaled to a unit circle. Now let's look at sine theta in the unit circle. In the right triangle, using a central angle theta, focus on the vertical side, the one that goes up or down. It is the opposite side of the angle theta. Since the hypotenuse, the radius, is 1, sine theta is just the length of that opposite side. That means sine theta directly gives you the y coordinate of the point on the unit circle. So when we say sine theta is a proportion or percentage, we mean it tells us how far up or down the point is on the circle compared to the radius. It's the vertical distance from the origin to the point on the circle. The unit circle makes trigonometry visual and intuitive, almost magical. In the picture, we see the unit circle marked with coordinate points at various angles of rotation. Each point represents an angle measured from the positive x-axis, and the coordinates are given as cos theta, sine theta, which are the cosine and sine values of the central angle theta. These values repeat every full rotation, or 2 pi radians, but their signs change depending on the quadrant in which the point lies. Within each 2 pi cycle, there are exactly 2 angles where both the cosine and sine have the same values, including sine. If we ignore the sine, there are 4 angles where the cosine and sine take on the same numerical values. The unit circle reveals this repeating pattern and makes the behavior of cosine and sine functions more intuitive and predictable. It helps to visualize the occurrence of the same values for sine and cosine within one cycle. Thus, sine 30 degree has same value and sine is sine 180 degree minus 30 degree, that is sine 150 degree, and sine minus 30 degree has the same value and sine is sine 180 degree minus 30 degree, that is 210 degree. And cosine 30 degrees has the same value, and sine is cosine 180 degrees minus 30 degrees, that is sine 150 degrees. And cosine minus 30 degree has the same value, and sine is cosine 180 degree minus 30 degree, that is 210 degree. On the unit circle, tangent values repeat every pi radians, meaning its values repeat exactly every 180 degrees. For example, tan 30 degree is equal to tan 210 degree, because 210 degree is 30 degree plus 180 degree. Similarly, tan minus 60 degrees is equal to tan 120 degrees, since 120 degrees is minus 60 degrees plus 180 degrees. This repeating pattern reflects the fact that tangent is the ratio of sine to cosine, and both sine to cosine repeat their signs and values in such a way that the tangent value recurs every pi radians. The sign of tan values change depending on the quadrant, positive in the first and third, and negative in the second and fourth. The picture shows how cosine and sine values turn positive or negative in different quadrants. Take cosine first. It's related to the x-axis. So whenever the x values are negative, like in the second and third quadrants, cos theta is also negative. The unit circle makes this very easy to see. Now for sine, since it relates to the y-axis, sine theta is negative in the lower half of the circle. That is, in the third and fourth quadrants, where y values are negative. The picture also helps us understand where tangent is positive or negative. Remember, tan theta is sine theta by cos theta. So, if both cosine and sine have the same sign, whether both are positive or both are negative, their ratio, the tangent comes out positive. If they have opposite signs, then the tangent is negative. That's just basic division rules at play. And the unit circle helps make it visually obvious. Our function is called even if its value stays the same when we replace x with minus x. In other words, function of minus x is equal to function of x. The graph looks the same on both sides of the y-axis. Trigonometric functions cosine and secant are even functions. A function is odd if flipping the sign of x also flips the sign of the output. That is, function of minus x is equal to minus function of x. The graph has rotational symmetry around the origin. The other four trigonometric functions, sine, tangent, cotangent, and cosecant, are all odd. The picture shows a few negative angles, and the listing explains their values clearly. What we need to remember is simple. Negative angles just mean we're measuring the rotation clockwise from the positive x-axis, instead of counterclockwise like with positive angles. But here's the key point. Even though the direction of rotation is different, the position on the unit circle often ends up being the same. So negative angles aren't new. They're just a clockwise way of reaching the same place. The unit circle makes that connection easy to see. This example shows that a given function value can be reached through both clockwise and anti-clockwise rotations, and even by making multiple full rotations. Angles where the sine value is half occur on the unit circle at both pi by 6 and 5 pi by 6. These two angles are in the first and second quadrants where sin is positive. But that's not all. We can reach the same sine value of half by rotating clockwise using negative angles, sine of minus 7 pi by 6, as well as sine of minus 11 pi by 6 is half. This shows that there are infinitely many angles that give the same function value, and the unit circle helps us visualize them all. The same sine value half can also be obtained by adding multiples of 2 pi to these angles, 2 pi plus pi by 6 or 2 pi plus 5 pi by 6. Or by subtracting multiples of 2 pi from these angles. 2 pi minus pi by 6 or 2 pi minus 5 pi by 6, 2 pi minus 7 pi by 6 or 2 pi minus 11 pi by 6. We now move on to an important topic. The trigonometric functions of the sum and difference of angles. To make sense of these functions, it's very helpful to visualize them on the unit circle. This approach offers a clear and intuitive understanding of how the functions behave. When solving trigonometric equations, a solid foundation in algebra is essential. Equally important are the geometric properties of triangles. particularly the rules of congruence like side, 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 angle, 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 side, angle, side, and right angle, hypotenuse, side. Also useful are similarity criteria, mainly based on the angle, angle condition. And finally, a word of advice: it's worth memorizing key trigonometric identities and results. They save time and reduce the number of steps in your calculations. Let's understand how to derive the cosine of angle difference formula, that is cos alpha minus beta. On the unit circle, point Q lies at an angle beta from the x-axis. So its coordinates are cos beta, sine beta. Point P lies at an angle alpha with coordinates cos alpha, sine alpha. The angle POQ formed between them is clearly alpha minus beta. Now, consider another point K, which lies at angle alpha minus beta from the x-axis. Its coordinates are cos alpha minus beta, sine alpha minus beta. Draw triangle KOA, where point A is on the x-axis at 1, 0. Here are the steps in that derivation. Here's the key idea. Triangles POQ and KOA are congruent, which means segments PQ and KA are equal in length. Now use the distance formula to calculate the lengths PQ and KA and set them equal to each other. From that, you arrive at the formula for cos alpha minus beta. In conclusion, the unit circle is incredibly powerful in visualizing and discovering trigonometric identities. It is truly a blessing. Of course, these identities must be committed to memory, but not through rote learning alone. The best way is through regular practice with problems. A few key identities should be understood deeply, their derivations explored and grasped. These become the building blocks for others, which in turn lead to even more identities. For example, take the identity for cos alpha minus beta. If we replace beta with minus beta and recall that sign is an odd function, we directly get the identity for cos alpha plus beta. Similarly, by substituting alpha with pi by 2 and beta with x into the same identity, we can derive the formula for cos pi by 2 minus x. In short, learning a few identities well opens the door to many others. Several other identities exist in trigonometry, and most of them are surprisingly easy to derive or remember once you understand the basic patterns. In this slide, we're deriving the identity for tan x minus y from the identity of tan x plus y. This gives us the final identity for tan x minus y, derived directly from the tan x plus y formula using a simple substitution. Here's a neat identity. Sine of double an angle, sine of 2x equals 2 tan of x by 1 plus tan squared x. It comes straight from the double angle formula. Just substitute sine and cosine in terms of tangent and simplify. Here's the triple angle identity for tangent. Tan 3x equals 3 tan x minus tan to the power 3x by 1 minus 3 tan squared x. It's derived by applying the angle addition formula twice. This form is especially useful in solving higher order equations or simplifying complex expressions involving tan 3x. Are trigonometric equations more tedious than algebraic equations? Not really, and perhaps even easier. Here's why. Would you agree? Based on the narrative in the 10 lessons. Here are my reasons. Thank heavens for the unit circle. It makes trigonometric identities and results not just abstract formulas, but clearly visual and geometric truths. Unlike algebra, where numbers can stretch to infinity, trig functions like sine and cosine stay nicely within bounds, between -1 and 1. That alone makes them far more predictable. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.